So now let's learn how to build and interpret a linear model. To do this, let's load the ArcData package once again. So it's already installed if you've worked through the plotting exercises that we had previously in a previous video. So you should be able to simply use the library function to call in the ArcData package to your current session. And let's make use of a specific data set within ArcData called barmos1.pp. If we use the data function here, it will load this data set into our environment. You can click on it, and that opens up the data set itself here so you can see what we're dealing with. This Barmos1 data set contains spatial coordinates, northing and easting values for a whole bunch of different artifacts from a site in Denmark, and kind of the labels for what type of artifacts these are. 473 different artifacts, I believe. Yes, if you look at over here, it says 473 observations. That's the rows of 4 variables. Those are the columns. So with this data set, we're going to build a model. So let's first, now that we've inspected that data set and we kind of saw that we've got 4 columns of the first 2 of the coordinates and the second 2 are of the different artifact types, I want to look at the actual kind of breakdown of all of these different artifact types and see what we're dealing with. And so to do that, I'm going to use the table function. With the table function, I feed it barmos1.pp, our data frame, $, denoting a column within that data frame, and label the name of that 4th column that contains the actual names of the different artifact types. And down here in our R console, we can see the output of this table function lists these different artifact types. We have 38 instances of scrapers, 25 of burins, 36 of lanceolate microliths, so on and so forth. So we've got different counts and different associated coordinates for a bunch of different types of artifacts. Now, for the model that we're going to build, I don't want to deal with all of these. I just want to get a subset of them. So let's make a new object. And into this new object, let's add just 2 of the artifact types that we have in the overall Barmos1 dataset. So let's index that data frame first by label, which is the name of the artifact. So we'll set the label equal to lanceolate microliths, which is just one of the types of artifacts that are included in this data frame. Now, if I put a comma there, this is saying, all right, take the barmos1.pp data frame and pull out every row, because we're in front of the column, or in front of the comma, pull out every row for which lanceolate microliths is the value in the label column. But as I said, we want to actually pull out 2 of the artifact types. So what I'm going to do now is type a vertical bar. This should be, if you hit Shift and hit the key above your Enter key, it should drop in that vertical bar. In kind of logical operations like we're using here within the indexing, that means OR. So we're saying now that we want each row for which label equals lanceolate microliths, or the rows for which the label equals scrapers. So now this code is indexing again just within that Barmos1 data frame, but it's pulling out the rows of lanceolate microliths, the rows of scrapers, both of those, because we're saying or lanceolate microliths or scrapers. Put a comma after that because this is all just the rows, and leave it blank after the comma because we want all of the columns of this data frame. Now if we run this, you can see that we've got a new object, barm.data.sub. If we look at that and scroll down, it just contains scrapers and lanceolate microliths. just the two artifact types that we're interested in at the moment. Now, since we've got the northing and easting data associated with these, let's plot that. Again, it's always a good idea to plot your data before you start modeling. Let's call it BARM data. That's what we call the new one. And I'm going to index within that data, say barm.data.sub. The label is equal to Lancelet microliths. So I'm doing this indexing within the data call so that I'm just going to plot the Lancelet microliths and their northing and easting coordinates. As I was saying, it's important to plot your data before you start building models and everything. You want to get a good sense just visually for what you're dealing with in your data. And so here I've plotted all of the Lancelet microliths of our subset of BARM data. And I plotted the northing coordinate as a function of the easting coordinate. Now, northing coordinates correspond to latitude, more or less, and easting corresponds to longitude. So you put northing on the y-axis, easting on the x-axis generally. And of course, at this site, they're not actually latitude and longitude. They're just spatial coordinates specific to the site itself. But it approximates latitude and longitude. And right here, now what we've got is just a map of all of the different locations of Lancelet microliths at this site. This is just going to show you that R can also be used to produce maps, and there's a whole set of GIS and spatial capabilities that R contains that we're definitely not going to get into, but they're there if you're curious. Now let's add the spatial coordinates of the scrapers. So again, barm.data.sub, and we want to index within that for barm.data.sub label, and the label is equal to scrapers. Remember to put a comma because we're still just getting the rows here. Let's add a color argument here. We're in this points function because we're going to add some points for scrapers on top of the plot we've already made for Lancelet microliths. So I want the colors to be different so it's not just a bunch of black dots and we can't tell which one's which. So if I run this points function, now we've got the scrapers plotted in red. And we can see kind of the spatial distribution of these two artifact types across this site. It looks like there's quite a bit of overlap between the two. Let's inspect that. If I run the summary on that indexed bit, here I'm copying the Lancelet microliths, and I'm going to copy that down into a summary function. Now, if I were to run this, that's all of the columns here. And really, I don't want all the columns. I just want to run it on, let's say, the easting column. So I type $east after the indexing. If this is difficult to see, right, it's barm.data.sub. That's the data frame. And then within the brackets, because we're indexing, I want labels equal to Lancelet microliths and all columns. But then after the indexing, after that close brackets, I put a $sign and just say east, because I'm going to pull out the east column. If I run summary now, we get these kind of summary statistics on that vector. If I run just what's in the summary, you can see it just spits out the east values for Lancelet microliths. The overall summary then, the median value 6.15, the mean 6.15 as well. Let's now compare that to the summary, not for Lancelet microliths, but for scrapers. If I run that, we can see that the median value is 5.42, and the mean is 5.5. Looking at the minimum and maximum values, it looks like there's a bit more spread for the scrapers, but the means and the medians are pretty similar to each other in terms of these easting coordinates. It seems like these two artifact types are pretty much on top of each other. But let's investigate that for real. Let's build a linear model. This linear model, as we discussed in the lecture on linear modeling, will allow us to statistically evaluate a null hypothesis, right? In the case of this model, because we're looking at lanceolate microliths and scrapers, and we're looking at the Easting coordinates of them, our null hypothesis would be that these data kind of come from the same distribution, that they're distributed the same way, that there's no effect of artifact type on Easting coordinate. And so to build a model then to investigate that null hypothesis, let's make a new object. We'll call it mod1 for model 1. And now we're going to use the LM function. This is the linear model function in R. If I pull up the help page for the LM function, you can read a description about it, what it's used for, and this is a very versatile function that's used to build a lot of different types of models. You can read all the different arguments that it takes. At the bare minimum, we're going to need to specify our formula, the x and the y data that we're plotting, and the data from which those come, potentially. And there's a bunch of other arguments that this model function can take. And of course, down at the bottom, then you'll be able to see examples of how to do this if you're ever uncertain or can't remember some details. But so for now, within this LM function, we're going to say east tilde label. That's east as a function of label, because we're going to be plotting the Easting coordinates on the y-axis and the label values on the x-axis. So it's going to be two different groups of data on the x-axis, microliths and scrapers, and the values that we're comparing between those two groups are the Easting coordinates. Now I specified data equals barm.data.sub so that it knows where I'm getting my data from. If we just said east as a function of label, there's no east object in our environment, no label object in our environment. So the function wouldn't know where to pull those. We need to specify data equals barm.data.sub. Now if we build this model, assign that output to mod1, we can inspect the mod1 object, which is now in our environment, and we can see the formula that we specified up here, and some of the coefficients. Now, the coefficients we'll discuss more in a second, but this is that structure of the linear model that we talked about in the lecture on that topic. You've got an intercept, right? And then you've got a slope. The intercept is where the regression line, the model fit, is going to cross the y-axis, and then the slope, rise over run, right, is the effect, in this case, of lanceolate microliths. The way that R does this is it assigns one of your categories, in this case scrapers, to be the intercept, and lanceolate microliths to the slope. We'll discuss this more in a second, but before we actually interpret this model too much, we need to actually make sure that our model is not violating any of the assumptions of a linear model. And if you recall from the lecture, there are 6 kind of key assumptions that we want to keep in mind. The first being that the model makes sense. We want to make sure that this model actually makes real-world sense, that we're not doing something that is resulting in weird values that you couldn't actually get in reality. Second, we want to make sure that the model is all additive. That's not going to be a real issue here. We want to make sure the model is linear. That will require inspecting the residuals of the model, which is what I'm going to show you now. We also want to make sure that there's independent errors, that there's homoscedasticity, that there's equal variance of those errors, and that the errors are normally distributed. All of these can be understood by inspecting the residuals of the model. And so what do I mean by that? Let's pull up a plot to do it. When you use the plot function on a model object, so mod1 is our model object, and if we include that in the plot function and run it, you can see that down here in the R console, we didn't actually get a plot in the bottom right, but we got a message down here that says hit return to see next plot. So if you put your cursor down here in the R console and you hit enter or return, the first of 4 plots gets pulled up. This plot is a plot of residuals of the model and the fitted values of the model. So the fitted values is representing the regression line, that best fit line that the model is fitting. And the residuals are the difference between each data point in your model and that line. Now, as we talked about previously, we want to make sure that our model is linear. And the way that you can tell that is if you've got a bunch of residuals in kind of a weird pattern, where it kind of would start below the line and go up and then come back down again, that might be suggesting that your model is not actually capturing what's going on in your data, that your model is linear but your data are not. And so that would be a violated assumption. But that doesn't seem to be happening here. And all we've got here is really two clusters of residuals because we're looking at categories of data. We're looking at the microliths and the scrapers. And so we also want to make sure that these errors are independent of each other, that there's no weird clusters of them, and that looks okay. There doesn't appear to be any real issue with independence. We also want to make sure that there's homoscedasticity. There's no issue with the errors suddenly becoming more spread out as the fitted value increases, for example. And it looks like these residuals, there's slightly more variance in this first case than the second, but it's really not terrible. It looks like we've got homoscedasticity, which is good. There's equal variance in the residuals. And we also want to make sure that the residuals are normally distributed around this. You can kind of get a sense for that in this plot. It looks like there's a lot of them here, kind of that bell curve shape. But in terms of discussing normality, there's a better plot for that. If we hit enter again, if we put our cursor down in the R console and hit enter one more time, we've now pulled up the second plot from this plotting of a model object. This is called a QQ plot, a quantile-quantile plot. In this plot, we've got the standardized residuals here on the y-axis and the theoretical quantiles on the x-axis. Don't worry about a lot of what these words mean, but this plot here, the point of it, is to allow you to assess the normality of your residuals. The dotted line here running diagonally across the plot that you can see, that represents normality. You want your residuals, your standardized residuals here shown in the black points, to fall along that dotted line. Now this can get a bit subjective. You've got some deviation of these residuals from that dotted line at low values and high values. Is that making a big difference? In this case, no. These residuals are not really that far from normal. I would consider this to be quite reasonable that we do have normally distributed errors in this case. Look at all these points falling along that dotted line. The minimal deviations up here at high and low values aren't going to make much of an impact on this. This QQ plot and the rest of these diagnostic plots, interpreting these is a bit subjective, and the more of them you see, the better a feel you'll get for whether this is a problem for your model and whether you should stop and find a different way to model your data. In this case, looking at that first plot, this looks good to me. These residuals are evenly distributed around that red line across the middle. And this QQ plot, these residuals are pretty well distributed along that dotted line, representing normality. If we go back then to our R console and hit enter one more time, now we've got a third plot. In this plot, we've got the standardized residuals where they've been transformed using a square root transformation, just meaning that instead of varying negative and positive values, now all the values are positive. It's just a transformation to make negative values all positive. And again, on the x-axis, we have the fitted values like we did in the first plot. And so in this plot, you can see that this red line is extending from your first set of residuals to the second. This is your model fit. And you want that red line to be horizontal. You don't want any change across the fitted values in kind of that distribution of your residuals. So as long as that red line is more or less horizontal, we're looking good. And again, these residuals, you can see that they're evenly distributed. They're looking pretty good around that best fit line. So this plot also looks good. And finally, the fourth plot that you can run is a plot called residuals versus leverage. Again, don't worry too much about all the details of what these plots are showing. There are numerous help files online that you can read about these diagnostic plots. But in this plot, it's showing the leverage of the residuals. if it's trying to investigate whether there are any perhaps outlier points that are really driving our model fit. And this is a plot that you could use to identify that. In this case, everything's looking really good. There would be points well outside of some confidence intervals shown in red, but this is looking so good the confidence intervals aren't even showing up on this plot. And so what we've just done is look at diagnostic plots for our model. As we've scrolled through these 4 different plots, we've seen, really based on, I think the first 2 are the most useful. They're the ones that I pay the most attention to. That the residuals are evenly distributed. There's no weird patterns going on here. Everything looks okay based on the assumptions of linear modeling that we discussed. And that there's no deviation from normality in this plot. If your diagnostic plots, these 4 plots, if they all look good, then you can proceed with interpreting your model. But if some of these plots aren't looking good, you're going to need to think about the assumptions that you're violating and perhaps change things up. And we'll discuss some alternatives to straightforward linear modeling in the future whenever these assumptions are violated. But for now, these diagnostic plots all look good. We are clear to move forward with interpreting what it is that our model is telling us.